Welcome everyone to the final chapters here in Math 132. This is integrals and applications. And like I mentioned here, right, we're bringing up the second big topic in calculus, and this is area under the graph of a function. And actually we're going to do a little bit of this here in Math 132, here calculus 1, but then in calculus 2 we're going to do a lot more of this. And actually we'll see, right, that this area under the graph of a function actually has something to do with derivatives. And so after we tackle this area under the graph of a function, right, we're going to go on and we're going to do area under more complicated functions. We're going to do area trapped between two functions. But you have to ask ourselves, why do we care about the area under a curve or under the function? And as usual, well, it has something to do, right, there's real world applications. And so I want to talk to you a little bit about the applications of this here in this video, right? So if f of x is a rate of change, so it's a function that tells you something about the rate of change, then the area under f of x on some specified interval, we'll say from a to b, is going to be the total change. From x equals a to x equals b, and as always, let's go ahead and kind of decipher what this means via an example. So I have a pump here that's delivering water into a tank at a specific rate, right? So this is 1 plus t over 2 liters per minute. And t is the time, it's given in minutes since the pump was turned on. And the question that I want to ask is how much water has been pumped during that first 6 minutes, aka what is the total change, right? How much water has come out of this thing, during that first 6 minutes. And so the above remark here says, right, we have some rate of change function, and if you consider the area under this function, under this f of x, on that specified interval, well, then you're going to get total change. So again, mine's a little bit different. I don't have x's, I have t's, right? So my independent variable is t. But you can see that I'm kind of interested in that first 6 minutes. This is going to be on the interval from 0 to 6. So t ranges between 0 and 6. And in fact, I have this kind of shaded down here. Right here is 0 all the way to 6. And if I calculate out this area right here, then I will get the total amount of change, the amount of water that has been pumped. Okay, so let's actually answer this question here. The nice thing about this graph, right, we have a nice straight line here, is that it makes a trapezoid, right? So this actually right here is a trapezoid, and we can have, right, where we can find an area formula for a trapezoid. But let's pretend, right, that I don't remember what the area formula for a trapezoid is. The nice thing about trapezoids is quite often they can be broken down into rectangles and triangles, right? So I'm going to go ahead and break this down into a rectangle and a triangle. And then I can calculate out the area this way. Okay, so let's go ahead and focus on this rectangle first. I'm going to go ahead and maybe shade this rectangle for us really quick. I'm going to find the area of this green bit right here. Okay, so the area of that rectangle, well, let's see, it has a length of 6. And I'd like to think about units for a second here too. So this is 6, but remember t is given in minutes, right? So this has a length really of 6 minutes. And then I want to figure out the height, right? So the height is given by this function right here, and it looks like it crosses here at 0, right? This is the correct height. And so if I was to plug in 0 into my function up here, the function that specifies heights, remember that this is my r of t, my rate of water pumping, and this is 1 plus t over 2. And so if I was to plug in t equals 0, that would give me the height out at time 0. That would be 1. So in this case, the height is 1 here. And again, let me think about units. Remember, this is given in liters per minute. So I'm going to go ahead and do liters per minute. And so if I wanted to calculate out that green area, right, so this would be 1 liters per minute times 6 minutes. And you can kind of see these minutes would perfectly cancel, right? One's in the denominator, one's in the numerator. And so I'm going to get a total of 6 liters, right? So this is the total that has changed, right? This is a total. It's not liters per minute anymore, but it's actual liters. All right, so that's the area of the rectangle. Let's go ahead and do the area of this triangle bit. So the area formula for a triangle is 1/2 base times height. So let's go ahead and figure that out here. So let's see, we're going to have 1/2. The base is still 6 minutes, so 6 minutes. And then times the height. So I need to figure out what is the height of this triangle. Okay, well, I can figure out the height of the overall function, right? The height of the overall function here. And that is, well, the function's height, right? So this is a point on the line when t equals 6. So I'm going to go ahead and calculate out r of 6 to get this line's height when t equals 6. So this is going to be 1 plus 6 over 2. That's a horrible way to write 2. There we go. So 6 over 2 is 3 plus 1. That's going to be 4. Again, this is spitting out liters per minute. So that's 4 liters per minute is the overall height. 4 liters per minute. But remember, I want the height of just the triangular bit. We have to subtract away this 1 liter per minute down here. So again, this is 1 liter per minute right here. 1 liter per minute. And so overall, that purple, the height of this triangle is 3 liters per minute. So the height of the triangle is 3 liters per minute. 3 liters per minute. Okay, again, we can see there's some nice cancellation. There's a minute in the numerator, there's a minute in the denominator. And so in this case, we're going to have 1/2 times 6, that's going to be 3, times another 3, that's going to be in total 9. 9 liters. So in total, if I add together the area of the purple triangle and the green rectangle, we're going to get a total of 15 liters. And so now we can see, right, the area under the curve, area under this function, it actually did something for us, right? We were able to calculate out how much water in total was pumped. It was 15 liters. And so area under a graph actually has real-world uses. And the claim is there are more. Right? Anytime you want total change, and maybe you have a rate of change, you can use this idea of area under a function, right? So suppose that maybe you have velocity and you want to know how much you were displaced, right? How much did you actually travel? Or suppose you have a rate of change of infection, right? And you want the total number of people infected. Or suppose that you have this idea of marginal profit, right? How your profit is changing, a rate of change for your profit, and you want the total profit, right? You have maybe how many dollars per day or something like this that you're earning, and you'd like to get the total profit. Again, this is going to be area under this curve, area under a function. Okay, so that's what we're going to be studying here in the last kind of big topic for Calculus 1, area under the graph. We're going to go into more detail about this when we hit section number 1. I'll see you then.